So this video gives you an overview of memory sizing on the Young supercomputer. This is part of a series of videos as part of the Young Events training. Please visit the website for more videos. In particular, we have a video which introduces you to using a supercomputer, as well as a range of software spotlights, which give you introductions to how to use specific software on the Young platform. So the aim of this talk is to summarise essentially how to specify memory sizing on Young, and this is partly in response to a number of jobs being run which are using essentially nodes without the full number of CPUs, partly due to incorrect memory sizing. So it's partly to address that, and also partly for new users to understand exactly how best to choose memory sizing. So if you take nothing else from the video, please understand three key points here. The job scheduler on Young is unusual for those of you who've commonly used supercomputers, in that it attempts to get your job running, without you worrying about the configuration. But in doing that, it will essentially allocate your job if you ask too much memory to extra nodes. And what this means is that your job, which maybe only requires 40 cores, will be spread over 80 cores worth of nodes in an attempt to make sure you get enough memory. So incorrect specification of memory will essentially result in underuse of the node. And this is bad because it will charge you more gold time, as well as block the resource for other users. It also means that your job will run suboptimally. An example here on the bottom right is basically allocation of different nodes, and what you see is only two of the cores are allocated to one node and the rest are on the other node. So this is an example where we only need 40 cores, yet 38 of them are on one node and only 2 of them are on another. So in order to combat this, the suggestion is that you check how many nodes your job is actually running, and this is good advice for people even if you're pretty confident you know what you're doing. Certainly for me, it was surprising that actually jobs that I thought would run on a single node were actually spread over 2. So commands such as nodes for jobs followed by your job number is very, very useful when a job is actually running. You should also get in the habit of just checking your host files, and these are of the form job name, .po, and then a job number afterwards to check which nodes are actually used during a job. You can also profile your job using user bin time for both, and from that you can see whether or not the memory requirements the job actually used are comparable with the actual resources that you request. And a third point to note from this video is that the nodes actually have a little less RAM than we expect. Now, the actual nodes on Young, as I'll talk about in this talk, are 192 gigabytes, but actually by the time you've taken into account the various operating system requirements, you end up with only about 180 gigabytes per node. So this suggests a limit of about 4.5 gigabytes per core that you shouldn't go above. If you do genuinely need more, then the 1.5 terabytes and the 3 terabyte nodes are available. But as I'll talk about in this presentation, you essentially will be in a particularly special use case if you're using much higher memory nodes, and generally most jobs of the type we expect to run on Young probably won't need more than 4.5 gigabytes per core. Okay, so let's start with just a quick specification overview for Young. We've got 23,000 cores on Young, which is spread over 576 nodes. These include mostly 40 core nodes, which have 192 gigabytes of RAM per node. And I'll explain exactly what those numbers mean for those of you who are kind of new to computers. And then we also have these large memory nodes, so 3 1.5 terabytes and 3 terabyte nodes. And then just the other thing to note is that each of these nodes essentially the cores use hyperthreading. So in principle, we have 40 cores, 40 physical CPUs, but those are split into 2 hyperthreads. So in terms of the charging, you're charged 80 processes worth. So that's 40 cores times 2. Okay, so first thing to understand is basically how a computer works. And that is essentially split into a hard drive, RAM and CPU in a kind of simplest model of this. And a typical computation essentially takes some numbers from RAM, which is the kind of short-term memory that the program uses, loads them into the CPU, does some calculation on them, and then saves those values back. And so the kind of workflow is that everything's done basically between the RAM and the CPU, and nothing should be written to hard drives. So what this suggests is that everything in your program should fit within the RAM of the computer. And hopefully that concept's familiar for your own workstation, and you're well aware if you go beyond the RAM available, your computer slows right down. So a supercomputer works in exactly the same way as your individual computer, where each node you can think of as being like an individual computer, and they're just connected together through high-speed interconnects. Okay, so each node is essentially 40 cores with its own dedicated 192 gigabytes of RAM. And there's a big disk that they all share, this kind of scratch base, but the whole point here is that, each individual node of 40 cores, 192 gigabytes of RAM, should essentially be kind of self-contained, and you should make sure the job fits within that node. So zooming on a single node, that's for 40 cores. You basically, for the job, for the memory requirement of those 40 cores, you shouldn't go over 192 gigabytes of RAM. And the key point here is loading from disk is very, very slow. And basically this means that, you haven't got the option, in general, of going beyond that RAM. And on a supercomputer, if you go beyond the available RAM, rather than going into a kind of swap space where it starts to use the hard drive, the job will just crash. So you need to make sure you allocate enough memory, or ask for enough memory to run your job. Okay, so before we go forward, let's just discuss the 3 types of parallelism, just so we know what we're talking about. OpenMP is a threaded model. So the idea is that each node within, say, so each core within your node, let's say there's 40 cores, or we can think of 80 threads with hyperthreading, so that's 2 per core, has essentially an OpenMP thread allocated to it. And generally the way this works is you would have a programming paradigm where they all share essentially the same memory. So all 192 gigabytes are available to all threads, and then they can just use that as they need to. The most common paradigm for supercomputers is the message passing interface, and so in this you create an individual set of processors, in this case M processors. This would be 40 if you're only running on one single node. So that's let's say 40 processors, and each of these has a completely individual memory. So the reason this is important is because it means that when you actually have 40 processes running on a single node, it means they each have to have their own individual RAM, which means 192 gigabytes has to be divided by the number of processes you're asking for. So that would be 192 divided by 40. And it's the same for job arrays. So this is really the third form of parallelism, where essentially you run, say, M instances, in this case 40 instances of the same program, and each of those is a completely individual program which has its own self-contained memory. So again, with the job arrays, you essentially can think of the requirement as being 192 divided by M. Okay, so with that in mind, let's have a look at a typical job script. Your job script, you have at the top the fact you want to use gold, and then the project allocation. This will be whatever your particular allocation statement is for your particular university or institute. You then request the amount of time you want it to run for. Here we've asked for 10 minutes. You request the amount of RAM per core that you want. Notice this is per core. So here we're asking for 1 gigabyte of RAM per core. We're specifying the name of the job, and then we're specifying we want to run on 40 processes. So this means that we'd run 40 processes, which will fit within one node. Each of those processes will have 1 gigabyte of memory, so that will use 40 gigabytes. That's underneath the 192 gigabytes on a node, so therefore this job will fit on a single node. You then specify the working directory. This would just be your ID and scratch base, and then you set the job to run. So the key point from this is the RAM. So with 192 gigabytes, 40 cores per node, this suggests we can have up to 4.8 gigabytes per core. So this is just dividing 192 by 40. So with that in mind, let's have a look at how big 4.8 gigabytes is, and this is useful for people who maybe these numbers seem a bit abstract. The conversion you just need to think about is a giga is 1,000 in science, but in computing that's always powers of 2, so we divide by 124 to get megabytes, 124 to kilobytes, and then down to bytes. So what this means is in order to get the number of bytes that 4.8 gigabytes includes, we basically multiply it by 124 cubed. The next thing we need to just be aware of in terms of understanding how big this is that typically a number on a computer program would be double precision, so that's 64 bits, and we have 8 bits to a byte. So typically that means that your 64-bit numbers are 8 bytes. And so in order to understand how many numbers we can actually get from 4.8 gigabytes, we take 4.8 times 124 cubed, so that's the number of bytes we've got, and divide it by 8. And this gives us a number that's basically 640 million double precision numbers per core. So let's take a second to just understand what that means. If you're running, let's say, a classical MD, molecular dynamics simulation, that means you have up to 640 double precision numbers available to you per core with this limit. So if you were going to run a simulation where you wanted to say stick 1 million molecules per core, it means you can have up to 640 kind of attributes of that molecule on a given core. Now classical MD simulations scale as n being the number of particles, and the memory similarly scales as n. So what this means is for a given MD simulation you'd want the position, velocity and acceleration. That might be 9n. There might be many others, but it's unlikely that you're going to have, say, 640 different bits of information for each of the molecules. And so what this means, realistically, and 1 million molecules per core is still excessive as well, is that it's unlikely for a kind of classical MD simulation that this memory limitation will be a problem. 4.8 gigabytes is very large. Similarly for say something like density functional theory, the CPU requirement scale is n cubed, while the memory requirements are actually n squared. So what this says is that actually you're generally going to be limited by the amount of compute you need rather than the amount of memory you need. And so again, what this means is generally what you're going to be wanting to do is actually to use more cores to run your computation faster, and it's not going to be memory that's the requirement. So it's only for very specific cases that memory is going to be the rate limiting step. Normally 4.8 gigabytes or even much less than this would actually be far more memory than you need. So with that in mind, it's very unlikely that you're going to want to request more memory than is available on the nodes, unless you have a particular case, and in which case you should be aware that this is kind of a memory bound problem and understand why. So then with that in mind, let's talk about how you actually estimate the required resources for your job script. Well, bear in mind, I said this before, I'll say it again, the job scheduler will request additional nodes if your RAM exceeds the available per core. So, the way to check whether this has happened is to use jobs for node with the job number, and this will tell you the CPU and memory and nodes that you're using. You can also look at host file after the job's run, check which nodes were used, and you can profile using user bin time. So let's give a kind of concrete example. If you request memory and number of processes, this is an MPI example, we ask for say 3.1 gigabytes of memory per process, and we ask for 40 processes. That means we're asking for 124 gigabytes. So that will fit within a single node. It's worth also noting that your actual limits here of 192 is actually slightly optimistic, and if you look at if you type in node types into the command line on Young, you'll see that actually the nodes we have got are slightly less. So this suggests that actually 4.7 is probably a more realistic kind of limit for the number of the amount of memory per node. Okay, so hopefully that's kind of made sense, but I want to just give you a kind of quick example of this to kind of to show you, how you can really understand these numbers. So this example is the simplest allocation of an array that you can do. So it's using MPI. So what this means is you initialize MPI and finalize MPI. The way MPI works is that everything between these two statements is run on all of the processes. So in this example, we're going to allocate and ask for 40 processors, which means everything done on here is run individually as a completely separate program on all of those 40 processors. Each of those has their own individual memory. Now the code here we've got basically asks for a variable of size 4.8 gigabytes. So that's 4.8 times 124 cubed. That's the amount of gigabytes divided by 8, which is the size of each of the individual numbers, and asked to allocate an array of that size. So this array is allocated basically to be the size of 4.8 gigabytes. And bear in mind that's going to be done for each of the 40 cores. So this is basically allocating an array, 40 arrays, of 4.8 gigabytes, which should be up to 192 gigabytes. We add in a loop here just in order that the job does something. So what you'll find with optimizing compilers when we compile this code is if you allocate an array but don't actually use it, it will skip allocating that. And you may notice this with your memory profiling. So we actually have to do something. In this case, it's just a dummy kind of loop where we just generate some random numbers and just put them into the array. So it just ensures that the amount of memory is actually allocated and that the job runs for long enough we can just check that memory allocation. So that's the example we're going to look at. Very, very simple. We compile it using MPI F90, which is just a Fortran MPI compiler. We could use C++ for this code, use MPI C++ instead if we were going to use that example. So don't worry too much about the actual details of the program. The key thing is this is just going to test an allocation of memory up to 4.8 gigabytes. Now our run script here, we specify on gold time. I'm using the Brunel allocation. I'm asking for 10 hours of wall time. I'm asking for 4.8 gigabytes of RAM, which is consistent with the 4.8 gigabytes I'm asking for in the program. I'm selecting 40 MPI processors, which means this will be run on 40 cores. This is my working directory, and I'm specifying I want it to be timed with GE run, running the executable AOut, which the script has been compiled to. So when we run that job, after we wait for it to queue, we look at QStat, and you can see that the QStat will tell us basically the job attributes. It's run on 40, we've asked for 40 cores, and there's nothing here in terms of its running that actually tells us that it's not running on a single node. And if anything, we actually see here that it just says a single node that it's running on. But when we actually do nodes for job, taking the job number here, what you see is actually it's spread over two separate nodes. And the reason it's done that is because actually by using 4.8 gigabytes, it doesn't fit on a single node, and so actually what the job scheduler has done is actually allocated two separate nodes. Now if we look at the host file for this, what you can see is that the way it's allocated it is that 38 of the CPUs on one node are being used, and then 2 CPUs on the other node are being used. So in other words, this is actually, rather than splitting the 40 core job into a kind of useful 20 and 20, it's actually just split 2 of them up just to give it enough memory that it can run. So this is clearly going to be a suboptimal arrangement. Especially if you have some sort of topology decomposition, what this means is that 2 of your processes will actually be sitting on a different node, and so the communication time between those is going to potentially be quite detrimental. And in addition, you're actually using only 38 cores on one, and then 38 cores are actually sitting idle on this node here. So again, in terms of use of resources, this is poor, and in terms of the actual distribution of the job, it's suboptimal. So this is certainly something you want to avoid. And the key point is that there's not enough RAM on a single node, so it had to be split over 2. It's partly because the RAM per node is actually slightly under the expected 192. So you're better to actually ask for no more than about 4 per core, and that should be plenty for most cases. If you actually do need more than that, then consider using the high memory nodes, the 1.5 or 3 terabyte nodes if not. And the RAM per node is 4.7 as mentioned, so if you actually look at the amount you've got, it is slightly under the 192. So let's try this example again. This time we're going to do a memory of 4.2, so we're actually going to use slightly under, and this should fit within that, and then we basically take a slightly smaller array. So we're just going to allocate an array that's about 4 times 124 divided by 8. And so we actually have a much smaller array allocated. We submit this to the job script, we check QStat, and you can see a new job number. Again, it runs, it looks exactly the same as the last job, but when we do nodes for jobs, you can see here that actually it's all run on a single node, 007, And then when we look at the host file, the .po file, you can see that actually it's all run on a single node using 82% of the memory. Okay, so the important point here is that actually it's not clear from the QStat or even the actual job submission that you would expect this to be split over 2 nodes. So you have to check things like nodes for jobs. You also have to check the machine files and make sure that it's doing what you expected. The final thing to mention is what actually happens if we ask for 4.2 gigabytes, but actually our array was of size 4.8 gigabytes. And so we didn't actually ask for enough memory. So this is exactly the same run script as we saw last time, but we just changed the program here. So this here is now 4.8 again. And what you'll see here is, that actually the memory from the user bin time.v, the maximum residual set size, this is basically profiling of how much memory was used, is 4.6 gigabytes, but we've only asked for 4.2 per core. And so what this means is you get basically an error message. This is a crash of our job. And essentially, this is not really giving much information of what caused that crash. And so really using some sort of profiling is important if you want to make sure that your memory requirements are not being overrun by this. But essentially this should be quite a rare example, because this is an example where we're using lots and lots of memory per core, something that shouldn't happen with most of the kind of use cases. Okay, so in summary, if you ask for too much memory, your job will be spread over extra nodes. This can kind of happen without you realizing it, and you'll be charged more gold time. You'll block the resource for other users, basically using, say, just 2 cores on a whole node with 38 sitting idly. And the actual job you run will be suboptimal, and your communication times will be much longer, and generally you'll get a much less good communication. And the point is, actually, this is not obvious when this happens. And so you basically want to make sure that you're checking your jobs. Even if it's a job you've been running for a while, just make sure that it's doing what you expect. Use node for jobs with the job number to see basically how many nodes you're running on, how many cores, and how many nodes you're running on. Look at the host file of finished jobs and just make sure that it is running on the cases you expect. And in this example, the evidence that it's actually split over 2 nodes, you can see that some of the cores are actually running on the second node. We wouldn't have expected that. And again, you can profile here to make sure that the memory requirements are under the limit you would expect. And just bear in mind that the limits are slightly under what you expect. So nodes have slightly under 192 gigabytes. I would suggest maybe assuming about 180 gigabytes per node as a kind of limit, and then not going above about 4.5 per core. So that's a memory statement of like -L memory 4.5. And then if you genuinely do need more memory, if you have a case where the memory requirement is vastly more than the compute time that you need, then consider using the 1.5 and 3 terabyte nodes if you do need that. But the point is, you will probably be using a very specific use case, and so you should know that you need those extra memory nodes. Thank you.